Hello Professor, I hope you are well in this pandemic situation. I am Dipankar Bala, student of the Department of Computer Science and Engineering, Islamic University, Bangladesh. I would like to be grateful to you for giving me the opportunity to present this presentation. Now I am presented a presentation of an article review that title name is a hierarchical bidirectional GRU model with attention for EEG-based emotion classification. Now I would like to tell you about the abstract findings that are the authors proposed a hierarchical bidirectional gated recurrent unit network with attention for human emotion classification from continuous electroencephalogram signals, that means EEG signals. They conduct the cross-subject emotion classification experiments on the deep dataset to evaluate the model performance. The experimental results show that in balance and arousal dimensions, their model on 1 second segmented EEG sequences outperforms the best deep baseline LSTM model by 4.2% and 4.6%, and outperforms the best shallow baseline model by 11.7% and 12% respectively. Now, for introduction finding, the findings are numerous studies in neurophysiology and psychology have found that the production or activity of human emotion is closely related to the dynamics of the cerebral cortex. Electroencephalogram is a general reflection of the electrophysiological activity of brain neurons in the cerebral cortex or scalp surface, which contains a lot of physiological, psychological and pathological information. They study the method of feature learning and representation of large-scale EEG data and then make emotion classification. Because EEG signals are highly time-dependent, non-stationary and susceptible to noise interference, it is a great challenge to design a model that can accurately predict the emotional categories of EEG. Now CNN, RNN, LSTM have been gradually applied to the modeling of EEG signals, but the research is still in its infant stage. Most of the current studies focus on emotion classification from subject-dependent EEG data rather than subject-independent EEG data, which instead is very important to develop a high-performance EEG-based effective human-machine interaction application. They propose a hierarchical bidirectional gated recurrent unit network with attention mechanism, which is called in shortly HATT-BGRU model, and the model is time varying EEG sequence recorded during external emotions stimulation. Now, for the hierarchical GRU model with attention, the hierarchical structure of their proposed HATT-BGRU model is shown in the left. This is the model, and this is the internal structure of GRU model. The proposed model is consist of EEG samples encoder, a sample level attention layer, and EEG epoch encoder and epoch level attention layer. Details of the architecture are discussed in the next slides. They applied a bidirectional GRU network for EEG sequence encoding. The GRU model is simpler and faster than the standard LSTM model. The GRU model is first introduced in 2014. The aim of this model to solve the vanishing gradient problem, which comes with the standard recurrent neural network. GRU can also be considered as a variation on the LSTM because both are designed Both are designed similarly and in some cases produce equally excellent results. Actually, GRU model is the improved version of standard recurrent neural network. To solve the vanishing gradient problem of a standard RNN, GRU uses so-called update gate and reset gate. Basically, there are two vectors. These are two vectors which decide what information should be passed to the output. The update gate helps the model to determine how much of the past information needs to be passed along to the future. The reset gate is used from the model to decide how much of the past information to forget. The GRU model able to store and filter the information using the update and reset gates. That eliminates the vanishing gradient problem. The bidirectional GRU networks extend the unidirectional GRU networks by introducing a second layer where the hidden to hidden connections flow in opposite temporal order. The model is therefore able to exploit information both from the past and the future. The architecture is shown in this slide. And now, hierarchical attention model. In order to apply the HATT-BGRU model, the EEG sequence is divided into several segments of equal lengths, each of which is called an epoch, and contain an equal number of time points which are called samples. The purpose of this model is to encode the raw ECG sequence into a vector representation on which to construct a classifier to make emotion classification. Now for the sample encoder, the cognitive activity of human brain is time varying. The occurrence time of the related EEG signals is also time varying. Now for the sample attention. Attention mechanism is introduced to extract samples that are important to the emotion of the epoch and aggregate the annotations of these informative samples into a vector representation of the EEG epoch. For the epoch encode, a vector representation of the EEG sequence can be obtained in the same way. For the epoch attention step, in order to reward the clue epochs that contribute to the correct classification of the sequence, attention mechanism is used again, and the epoch level context vector is introduced to measure the importance of the epoch. For the sequence classification, the obtaining vector is a high-level feature representation of EEG sequence, which is more discriminative and robust. Therefore, it can be classified by softmax function. The model is trained by minimizing the cross-interval loss function between the predicted level and the real level. The model is also trained with Adam optimizer. And for the experiments and results, firstly, they introduce the deep dataset and easy data pre-processing methods. Then they evaluate the effectiveness of their model compared with other baseline shallow classifiers and other deep neural networks through cross-subject binary emotion classification experiments in valence and arousal dimensions. For the easy dataset, the experiments are performed on deep dataset, and this dataset is public dataset, and this dataset is developed by researchers at the Queen Mary University of London, which is a large open source dataset containing multiple physiological signals with emotional evaluations. The dataset records EEG, ECG, EMG and other bioelectrical signals, while 32 subjects were watching 41-minute music videos with different emotional tendencies. The subjects then evaluate the videos with emotion scale from 1 to 9 in dimensions of valence, arousal, liking, dominance, and familiarity. The 40 stimulus videos consist of 20 high valence arousal ones and 20 low valence arousal ones. And now for the data processing, they extract the first 32 channel EEG signals from deep dataset, downsample the data to 128 Hz, filter the data with a band fast filter of 4 to 47 Hz to eliminate the background noise, make common average referencing and remove the ocular artifacts by blind source separation algorithm. The total length of the preprocessed EEG signals is 63 seconds, including 60 seconds of watching video and 3 seconds before watching. The authors then removed the 3-second baseline signals average from 60-second EEG signals of watching video and normalized the data cross-channel to acquire the normalized stimulus related dynamics. Next, in the time domain, the 60-second EEG sequences are segmented into 61-second epochs. The size of each subject's dataset is 40 trials multiply 60 epochs multiply 28 samples multiply 32 channels, and each trial corresponds to an EEG sequence. Based on the emotional rating value of each video in scale of 1 to 9 in arousal and valence domain, the median 5 is used as the threshold to divide the rating value into two categories. The value more than 5 is labeled 1, that means high arousal or valence, and the value less than or equal to 5 is labeled 0, that means low arousal or valence. Finally, the levels with size of 40 multiply 1 for each subject are obtained. To evaluate the performance of our model on different length epochs, they also segment each EEG sequence into 120, 24 and 12 epochs with the length of 0.5 second, 2.5 second and 5 second respectively. Therefore, each epoch contains 64, 320 and 640 samples, and each samples contain 32 channel data. This segmented EEG data in time domain as raw features of each subject, and the size of raw features in different length epochs is shown in table 1. And now for the shallow classifiers. They use the shallow classifiers including bagging tree and supported vector machine, that means SV, which have shown good performance in EEG-based emotion recognition as baselines. Because the shallow classifiers cannot self-learn the high-level discriminant EEG features, they extract the features of autoregression and power spectral density respectively, make feature selection and then perform binary emotion classification in valence and arousal. Finally, the first 6 maximal autocorrelation coefficients of each channels are taken as autoregressive features of each epoch, and the total autoregressive features are size of 2400 epochs multiply 6 autoregressive features multiply 32 channels. Now, deep neural networks. They also explore two popular deep neural networks including CNN and LSTM, that means convolutional neural network, and long short-term memory model to make cross-subject emotion classification as 1 second raw features of deep dataset as baselines. The CNN model regards each 1 second EEG epoch as an image of 128 samples multiply 32 channels as the input. The total number of EEG epoch of 32 subjects is 76,800. So, as the number of levels. They randomly select the epochs of 8 subjects, that means 25% of total, as the test data. and the epochs of the raised 24 subject, that means 75% total data as training data. The tenfold cross-subject cross-validation sets are constructed to train the CNN model. The structure of the CNN and LSTM model is shown in below. First is CNN model and second is LSTM model. And now for the configuration of ACE-ATT-BGRU model, they trained their ACE-ATT-BGRU model on tenfold cross-subject cross-validation datasets of EEG sequences with 1 second epochs and test its binary motion classification accuracy in the valence and arousal. Each sample is a 32 channel feature vector which is similar to each word is represented with a 32 dimension word embedding vector. At last, the vector V is fed into the softmax layer to predict the emotional category. In training, mini-image size is set to 60, which means 60 sequences are organized to be a batch. It is also the number of epochs in each sequence. The model is trained with Adam optimizer with the learning rate 0.05. Now, result and analysis. The experimental results of different models on 1 second raw features of deep dataset in valence and arousal are shown in the following tables. In this article, they extend the hierarchical bidirectional GRU network to ACE-AVE-BGRU model and ACE-MAX-BGRU model. The ACE-AVE-BGRU model taking the average of sample or epoch annotation output by GRU as the aggregation feature vector of the epoch, and the ACE-MAX-BGRU model takes the maximum of sample annotations output by GRU as the aggregation feature vector of the epoch, while their ACE-ATT-BGRU model aggregates the sample annotations with their context-weight vectors to generate the epoch. From the left table, their proposed model gets the best classification performance of 66.7% in valence and which outperforms the best shallow baseline BT model by 11.7%, outperforms the best deep baseline LSTM networks by 4.2%, and outperforms ACE-AVE-BGRU model and ACE-MAX-BGRU model by 2.3% and 2.1% respectively. Their proposed model achieves the optimal classification accuracy of 66.5%, which is 12.0% higher than that of the best shallow baseline SVM model, 4.6% higher than that of the best deep LSTM network, 2.1% and 2.2% higher than those of ACE-AVE-BGRU model and ACE-MAX-BGRU model respectively. Right side figures show the comparison of performance of different models on 1 second segmented EEG sequence. Following table and figure show the comparison of performance of different models, the length of epochs. The left table show the classification. The left table show the classification accuracies. Four models are consistently improved with shortening the length of epochs. Here the proposed model also achieved the best classification accuracy of 69.3% on 0.5 second segmented EEG sequences. The right side figures show the performance comparison for the different length of epochs result. The proposed hierarchical model with attention mechanism can learn more significant and dependent feature according to the context importance weights at both sample and epoch levels to overcome the non-stationarity of EEG sequences and therefore improve the classification accuracy and robustness. And finally, for the conclusion and future words, we can say that in this paper they propose a hierarchical bidirectional GRU model with attention mechanism, that means HATTB-GRU model for learning EEG sequence features and making cross-subject emotion classification on them. The model uses attention mechanism at both sample and epoch levels. The proposed model can effectively reduce the impact of long-term non-stationarity of EEG sequences and improve the accuracy and robustness of EEG-based emotion classification. The model will be applied to develop the applications of robust, effective brain-computer interface in the future. And thank you.